Hello students and welcome to the lecture. So students, as we know that in the previous lecture we had started our discussion over the viscosity, right? And that was our part 1. In this lecture we are going to start the part 2. In the previous lecture we had talked about what do you mean by the viscosity, how it is different from solid friction, what is Poisson's formula, Stokes law and the terminal velocity. In this lecture we will take the discussion points as variation of viscosity, streamline, laminar and turbulent flow, Reynolds number, equation of continuity. Okay, we are going to discuss on this. Variation of viscosity, streamline, laminar and turbulent flow, Reynolds number, equation of continuity. But before starting this lecture, there is a small disclaimer that we are required to understand before we proceed further. The disclaimer is like the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this text and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. Now let's begin with the variation of viscosity. So if we just revise that what we have learned in the viscosity, so we could say the viscosity is actually a property of fluid. And when we say fluid, we are not only talking about the liquid, but we are taking the liquid and gases in the consideration while we are talking about fluid as per the science. Okay. So basically, viscosity is the property of fluid by virtue of which it having the internal resistance or you can say friction to oppose the relative motion between the different layers. Okay. And now we will talk about like how does the property varies because of some factors. The first factor that we are going to discuss is the effect of temperature. So with increase in temperature, the viscosity of liquid decreases. How? Let's have a discussion on that. So basically we know the viscosity is primarily presents because of the intermolecular force. Okay, like the molecules inside the different layers having the intermolecular force, that's why they are having the backward dragging force to oppose the relative motion between two. And whenever the temperature goes high, generally it decreases the intermolecular force because it is increasing the kinetic energy of the molecule particles. So that's why the relative motion between the two layers is increasing because the backward raising force is getting on decrease. So that's why whenever the temperature goes high, the kinetic energy goes high. So the intermolecular force reduces, automatically the viscosity of liquid decreases. The viscosity of all gases increases with increase in temperature. Now you can say this is contradictory to each other. In liquid, where we were saying that basically as the temperature is getting increased, the liquid viscosity decreasing. The same case is not applicable when we talk about gas. In gases, all the gases, not the specific gas, all the gases, as the temperature increases, the viscosity also increases. Instead of decreasing in that case, it is increasing. And this is because since the viscosity of a gas is directly proportional to the square root of the absolute temperature. That's why at a directly proportional to under root T. Under root T means under root temperature. Okay. So because of this statement, sorry, not this, this statement, it is happening in all gases that viscosity is increasing with the increase in temperature because the viscosity of gases is directly proportional to the square root of the absolute temperature. Or we could say at a directly proportional to under root T. This result is obtained from the kinetic theory of gases. So if anyone asks you like why this is happening, so just say because of the kinetic theory of gases. Okay. Now What is the effect of pressure? This is the second factor that gives the variation of viscosity. Okay, so with increase in pressure, the viscosity of liquid increases. Why? Because the pressure actually increasing the intermolecular force, encouraging it, and the backward rising force also getting encouraged. So because of this encouragement, the relative motion between the two different layers is continuous on oppose or continuous on decreasing. So that's why with the increase in pressure, the viscosity of liquid also increases. But the water, which is also the liquid, in this scenario, it is again the contradictory form, because as the liquid increasing the viscosity with increase in increase in pressure, water is decreasing the viscosity with increase in pressure. Water is alone a liquid which is having the capacity to decrease the viscosity with increasing the pressure, whereas the viscosity of gases remain unchanged. So we could say if we are having the case of gases and we are increasing the pressure, so the pressure will have no effect on the viscosity of gases because it is unchanged. Now, practical uses of the knowledge of viscosity. Like, what are the practical uses of knowledge of viscosity that is we required to understand? First, the knowledge of viscosity and its variation with temperature actually help us to select a suitable lubricant for a given machine. Okay, that's the first scenario. Second, the knowledge of viscosity of some organic liquids like proteins and cellulose, etc., help us in determining their shape and molecular weight. Like we could say, without, or you can say with some normal means, we are not able to determine the shape and molecular weight of these organic liquids because of their microscopic capacity. So that's why we could have the knowledge of the viscosity through which we could determine their shape and molecular weight. Okay. Now, at railway terminals, you could say the liquids of high viscosity used as a buffer. Okay, like if you look at it here, you will see that these are the buffers. Okay, and basically inside this, there is a liquid which is having a high viscosity. Okay, why it is happening? Because if they are having the high viscosity, automatically the relative motion between the different layers of this liquid will be opposed due to the backward driving force. So when the train came and hit this, so basically they could easily oppose the relative motion and the train will face a external force from them and would be stopped. Okay, and on the other hand, if they will be on the normal or low viscosity, so they could be easily dragged back and the train will hit this spot and the damage will be a more. But because they are opposing the relative motion, so that's why they are exerting a force on the train which is contact with these buffers, and the train will experience the external force and will stop. The knowledge of viscosity helped Millikan in determining charge on an electron. Motion of some instrument is damped by using the viscosity of air or liquid. The phenomenon of viscosity plays an important role in the circulation of blood through arteries and veins of human body. Like we could say, the knowledge of viscosity is just not only usable in the case of physics and chemistry, but also in the case of biology. Because arteries and veins and the medicality of the human body is the part of biology, not only the part of physics and chemistry. So we could also use the phenomenon of viscosity there. Now, let's have a discussion over the streamline, laminar, and turbulent flow. Let's start with the streamline flow. The streamline flow of a liquid is that flow in which every particle of the liquid follows exactly the path of its preceding particle, having the same velocity in magnitude and direction as that of its preceding particle while crossing through that point. For example, if the one particle crossed this point, okay, then another particle will also cross this point. with same velocity in magnitude and with the same direction. Okay, so the magnitude, direction and the path will not be differed from particle to particle, and when this case happens, it is known as the streamline flow. When the preceding particle when the particle exactly following the same path, same velocity, magnitude and same direction as the preceding one, while crossing through that particular point from where the preceding particle had crossed, then it is the streamline flow. The streamline flow is accompanied by the streamlines. That's why it is known as the streamline flow. A streamline is the actual path followed by the procession of particle in a steady flow, which may be straight or curved such that tangent to it at any point indicates the direction of flow of liquid at that point. Here you can see. Now you will see every dot is in the same direction with same velocity and magnitude and following the exact same path in comparison with their preceding particle, right? That is the thing. Now, important properties of streamlines. What are the important properties? Like we know streamlines are basically the part of the streamline flow. Now, what are their properties which are important from the examination point of view as well as our knowledge point of view? First, in a streamline flow, no two streamlines cross each other. If you look at this picture, you will see that there are 1, 2, 3, 4, 5, 6, 7. 7 streamlines you could see here. What you are seeing? What is the flow of these streamlines? Are they crossing each other? No. They are parallel to each other. They are not intersecting, not crossing each other's path, but they are parallel to each other. That is what we call as a streamline flow. Okay, so first property is that streamlines will not cross each other's path. They will follow a independent path or parallel path to each other. Second, if they do so, the particles of liquid at the point of intersection will have two different directions for their flow, which will destroy the steady nature of liquid flow. Like if they crossed each other parts, so the particles of liquid at that point of intersection will have the two different directions. For example, if we consider this, that it is moving in the east direction, this north, this south, this west, east direction. Okay, so if this line crosses this line, so this line having the direction to the east, but this line will have the direction to the southeast. So you can say the two different direction case is there. That's why they are intersecting each other's path. And whenever this happen, then the steady nature of liquid flow will be destroyed. And this is the condition for streamline flow. If this steady nature of liquid flow destroys, then that will not be a streamline anymore. The greater is the crowding of streamlines at a place, the greater is the velocity of liquid particles at that place and vice versa. Okay, so if the crowding of streamlines at a place higher, the velocity of liquid particles higher. If the crowding of streamlines at a place lower, velocity of liquid particles also lower, because it is the vice versa case. Now, tube of flow, that is another thing. A tube of flow is actually the bundle of streamlines having the same velocity of the liquid particles over any cross section perpendicular to the direction of flow of liquid. Then it is known as the tube of flow. It has been seen that the flow of liquid will be streamlined if the velocity of liquid flow is always less than the critical velocity of the liquid. So what do you mean by the critical velocity? Let me tell you. Critical velocity is that velocity after reaching that point, the flow will become turbulent. Okay, so the velocity at which the flow transformed from streamline to turbulent is actually the critical velocity. As long as the flow of liquid is below or less than this critical velocity, the flow will be streamlined. That flow will be streamlined. But once it crosses the critical velocity of the liquid, the flow will become turbulent and no longer an streamline or steady flow. Okay, but what is the value of critical velocity? Like when we say critical velocity is actually that velocity which could transform the flow from streamline to turbulent. That is what we are saying. But what is the value? How do we know that this is the velocity or critical velocity? We have to keep the flow below this velocity. How? We must be able to calculate the value. That's it. By calculating the value only we'll be able to do it. Okay. So the question is the value of critical velocity is same for all kind of liquid or different for all kind of liquid? So remember, the value of critical velocity is not same for all the liquids, is actually different for different liquids. For example, if we having a 5 liquids, liquid A, liquid B, liquid C, liquid D and liquid E. Critical velocity for all the liquids will be different. Critical A will have different velocity from B, C, D, E. Similarly, B will having a different velocity from A, C, D, E. Similarly, C will having a different velocity from A, B, D, C, sorry, D, E. D also from A, B and C, E. E also from A, B, C, D. All of them will having a different value of critical velocity. Okay, there is nothing like the value will be same. Now, finishing the streamline flow, let's have a look on the laminar flow. If a liquid is flowing over a horizontal surface, having a steady flow and moves in the form of layers of different velocities, which do not mix with each other, then the flow of liquid called the laminar flow. Here you can see it. Now you will see that this is having the highest velocity, then this is lower, this is lower, this is lower, this is lower. Okay. So now you can say they are having the different velocities. Okay, their velocity is different. But another condition is that they do not mix with each other. Are they mixing with each other? Could you see it? No. They are not getting mixed with each other. Okay, this is not intersecting this path, this. No one is intersecting each other part, which means they are not getting mixed with each other. They are flowing parallel to each other but with the different velocity. So that's why we could not call them as the streamline flow, because the condition for the streamline flow was same path, same velocity, same direction. Okay, here we having the same path, or maybe we having the same direction, but we are not having the same velocity because they are flowing parallel to each other. Okay, but with the different velocities. So that's why we call them as a laminar flow. In this flow, one layer slides over the other layer of liquid. In this flow, the velocity of liquid flow is always less than the critical velocity of the liquid, because if the velocity of liquid flow becomes higher than or equal to the critical velocity, automatically this laminar flow transfer to the turbulent flow. And as long as it is lower than it, it is laminar flow. In general, laminar flow is a streamline flow, but the condition of having the same velocity is not applicable here. Okay, this condition is different. Turbulent flow. Okay, so when a liquid moves with a velocity greater than its critical velocity, the motion of the particles of liquid becomes disorderly or irregular. Such a flow is called the turbulent flow. So now, the thing that I am saying you again and again, it is actually confirming here. Like when the velocity of liquid becomes greater than the critical velocity, the motion of particles of liquids remain no in order or regular. They become disorderly or irregular. So then the flow becomes a turbulent flow. It is no longer a streamline or laminar flow, but now this is known as the turbulent flow. Okay. What is the critical velocity exactly? What is it? So the critical velocity is actually the velocity of liquid flow up to which its flow is streamlined and above which its flow becomes turbulent. So for example, if we say 10 is the critical velocity for only example. So if the flow is at 8, at 9, even at 9.9, lower than the critical velocity, that will be a streamline flow. But once it's become 10.5 or 10.1, even 10.1, then it is more than the critical velocity. It will become as the turbulent flow. No longer a streamline flow, but becomes a turbulent flow. The critical velocity Vc of a liquid flowing through a tube depends upon what is the coefficient of liquid, density of liquid, radius of the tube. These three factors actually defines the critical velocity. Why? Because critical velocity depends on them. Now let's have a discussion over the Reynolds number. What do we mean by this Reynolds number? So Reynolds number is actually a pure number which determines the nature of flow of liquid through a pipe. Okay, like if you see a pipe, the flow you are seeing of liquid. So what is the nature of flow of liquid? That could be defined by the Reynolds number, because by seeing the flow you couldn't be able to define that whether it's a laminar flow or turbulent flow. Okay, according to Reynolds, the critical velocity Vc of a liquid flowing through a tube of diameter d is given by Vc equals to Ng eta by Pd, or Ng equals to PdVc by eta. When eta is the coefficient of viscosity of the liquid, P is the density of liquid, and Ng is constant, which we called as the Reynolds number. Got it? The value of Reynolds number Nr is independent of the system of units used for the measurement of various quantities in equation. This is an important statement. Remember, again I am repeating it. The value of Reynolds number is actually independent of the system of units that we generally use to measure various quantities in equation. If the value of Reynolds number lies between 0 to 2000, the flow of liquid is streamline or laminar. If the values of Ng becomes above 3000, the flow of liquid becomes turbulent, and for values of Nr between 2000 to 3000, the flow of liquid is unstable, changing from streamline to turbulent flows. So these are the values. Okay, if the value of Reynolds number lies between 0 to 2000, the flow of liquid is streamline or laminar. If the values of Ng above 3000, the flow of liquid is turbulent, and if Nr having a value range between 2000 to 3000, the flow of liquid is unstable and changing from streamline to turbulent. Okay. Now the equation of continuity. Consider a non-viscous liquid in a streamline flow through a tube AB of varying cross section. Here you can say it's having a varying cross section. Let A2 into A2 equals to area of cross section of the tube at A and B respectively. V1 and V2 equals to velocity of flow of liquid at A and B respectively. P1 and P2 equals to density of liquid at A and B respectively. Volume of liquid entering per second at A equals to A1 and V1. Mass of liquid entering per second at A equals to A1, V1 and P1. A into V1 and into P1. Okay. Similarly, the mass of liquid leaving per second at B equals to A2 into V2 into P2. If there is no source or sink of the liquid along the length of the pipe, the mass of the liquid crossing any section of the pipe per second must be the same. Thus, we have A1 into V1 into P1 equals to A2 into V2 into P2. Equation of continuity continued. Practically, the liquids are incompressible. Therefore, P1 equals to P2 equals to P. Say, therefore, A1 into V1 into P2 equals to A2 into V2 into P2, or A1 into V1 equals to A2 into V2, or AV equals to constant. This is known as the equation of continuity. From above equations, we could say V is inversely proportional to 1 by A. It means the larger is the area of cross section, the smaller will be the velocity of liquid flow and vice versa. So we could say if the area of cross section is larger, the velocity will be smaller. If the area of cross section is smaller, the velocity will be higher. It is due to this reason that I, deep water runs slow or slow water runs deep P. The set of falling water becomes narrow as it goes down. With this, we have finished this lecture. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.